Okay, for our solution for this problem, you can have letter A. So what will be the vertical effective stress at point A before lowering the water table? So basically for this, we try to get for the effective stress at point A before lowering the water table. The point A is on the mid-height of the clay layer. So half of this portion of the clay layer, so that is the location of point A. So for this one, for this solution, he immediately get the effective stress by subtracting the unit weight of the water to the saturated unit weight multiplied to its depthness of that particular layer. So for this one, this is point A. So basically, before lowering the water table is on the ground surface. So at point A, that would be at the mid-height of the clay layer, so 12.5 times the quantity of 120 minus 62.4, that's the unit weight of the water, then plus, that would be plus 135 for this sandy type soil, subtracted by the unit weight of the water, 62.4, times 50, which is the height towards this portion, this layer, which is 50, so you get 4,350 pounds square feet. Or to get the effective stress, you can have first compute other solution to have a more clear understanding. You can compute first for the total stress. Once you compute for the total stress, compute for the neutral stress or the pore water pressure. Once you have the value for the total stress and the pore water pressure, you subtract the the pore water pressure from the total stress, and you get now the value for the effective stress. Meaning to say, effective stress is equal to total stress minus pore water pressure, and you have now the value for effective stress at any point. So other solution to this, meaning to say, if you try to get the total stress at point A, so you simply have 120, we're trying to compute for the total stress, 120 times 12.5 plus 135 times 50. And you have the equivalent value of the total stress, which is 8,250. And if you try to get now the pore water pressure is on the ground surface, or water table rather. The water table is on the ground surface. So basically, to get the pore water pressure at point A, that would be the height of the water from point A towards the water table. So from point A towards the water table, that is 12.5 plus 50. So that will be equivalent to 62.5. That is the height of the water table towards point A times the unit weight of the water. Since we are in pounds, so times 62.4. And the value to that is equal to 3,450. So that is the value for the pore water pressures. Then you can get now the value for the effective stress at point A before lowering the water table. That will be effective stress now is equal to total stress minus pore water pressure. So the value of the total stress was 8,250, subtract by 3,450, you get a value of 4,350 pounds square feet. So you save the same value for the effective stress, just have an alternate solution to have a more accurate solution for your for getting the effective stress. Now for letter B, what will be the effective stress at the midpoint after of the clay layer after lowering the water table? So for this one, if we try to get the value for the effective stress at point A after lowering the water table, we have to get first, when you try to lower the water table, you lower the water table by 25 feet, and the degree of saturation as we lower the water table was lowered by 20%. So meaning to say, we have to get your unit weight for this one as we lower the water table. So that would be equivalent to 116 that is the dry unit weight, then plus this one, you subtract 135 minus 116 times the 20% lowering of the degree of saturation. So it gives us 119.8 pounds cubic feet. So that is our unit weight after we lower the water table for this portion. Then we try now to get the effective stress at point A after we lowered the water table. So this is the solution. This solution actually is a direct method to solve for the effective stress. And you can also, there is an alternative as presented a while ago. Still, the value is 5,530 pounds square feet. So meaning to say, if we want to get the total stress at point A, that will be equivalent to 12.5 times 120 times this one, 120 plus 135 times this one is 25, then plus this is 25 times this unit weight, which is 119.8, and we get a value of 7,870. So get now the pore water pressure. The pore water pressure at point A will be the unit weight of the water in pounds is 62.4 times the height from point A, from this point towards this one, is 25 plus 12.5. So that will be equivalent to 25 plus 12.5 times 62.4, the unit weight of the water, and the value to that for the pore water pressure is 2,340. Then if we try to get now the effective stress at point A after lowering the water table, you subtract. You subtract the total stress minus the pore water pressure, 7,870 minus 2,340, it gives us 5,530 pounds square feet. And the last one, what will be the vertical stress effective pressure at point A when there is no water table on the sand layer? Meaning to say there is no water on this portion of this layer, on the sand layer. So basically, you get now, this is now the effective pressure at point A if there is no water table in the sand. So if we try to get another solution to this, let's have the computation for the total stress at point A. So that means equal to 12.5 times 120 plus there is no water in this area, so we're going to use the unit weight that we have computed a while ago, which is 119.8. So meaning to say, we're going to have 120 times 12.5 plus 119.8 times this one is 50. And it has a result of 7,490. That is the total stress. And if we try to get the pore water pressure at point A, that will be 62.4, the unit weight of the water, times 12.5. The water table is only on this portion. There is no water on the sand, so that will be the pore water pressure would be 62.4, the unit weight of the water in pounds, times 12.5, that is the height of the water table towards point A, and it gives us 780. Now, to get the effective stress at point A when there is no water table in the sand, you subtract total stress and the pore water pressure. So that will be 7,490 minus 780. So that is, the result is 6,710 pounds square feet. So that is for this problem. So we have here another example. A 20 thick submerged saturated clay layer has a water content of 57%. The specific gravity of the solid particles is 2.84. Determine the density of the clay in kilogram per cubic meter. We're going to determine the total vertical stress at the bottom of the clay layer in kilopascal. Determine the effective vertical stress at the bottom of the clay layer in kilopascal. So for this one, the thickness of the saturated clay is 20 meters. It has a water content of moisture water content of 57%. We're given with specific gravity of the solid, which is 2.84. So determine the density. So since we are given only with the specific gravity, we'll try to compute first for the unit weight of the clay layer. So that will be equivalent to use our previous formula. Specific gravity times moisture content is equal to degree of saturation times E, which is void ratio. This will be unknown. So we're given with specific gravity, moisture content. And for this is saturated. So our degree of saturation is equal to 1. So if we try to substitute to this equation, our void ratio is 1.6188. Then we can now get our unit weight of the saturated clay. So using this relationship, this equation, specific gravity plus degree of saturation times void ratio over 1 plus void ratio times the unit weight of the water. So basically, if we try to substitute our given parameter values, we get now the density of the saturated unit weight, which is 16.7026 kilonewton per cubic meter. So we're trying now to determine the density of the clay in kilogram per cubic meter. Of course, density is the unit weight over our specific gravity. So it gives us 1,702.6 kilogram per cubic meter. And we get now the total stress. So for the total stress, that will be the unit weight of the saturated clay times the height. So we have computed the unit weight of the saturated clay, 16.7026 times the height is given, which is, it has a thickness of 20 meters, so times 20. So the total stress now is 334 kilopascal. Now we are trying to get the effective stress. Of course, effective stress, as mentioned a while ago, that is equal to the total stress minus our pore water pressure. So the pore water pressure for this actually is 20, that is the height of the saturated clay, times the unit weight of the water, which is 9.81. So we subtract this to the total stress, which is 334. So the effective stress now is equal to 137.85 kilopascal. So this is now the effective vertical stress at the bottom of the clay layer. So we move on now to stress in saturated soil with seepage. So for this one, we have for stress in saturated soil with seepage, we have two categories. We have upward seepage and downward seepage. When we talk about upward seepage, if water is seeping, the effective stress at any point in a soil mass will differ from that in a static case. It may increase or decrease depending on the direction. So for this one, for the stress in saturated soil with seepage, we have here a figure showing you have a granular soil in a tank. This is a granular soil within a tank where upward seepage is caused by adding water. There is an upward seepage caused by adding water through the valve at the bottom of the tank. So this is the tank. There is a granular soil inside the tank. So there is an upward seepage that is caused by adding water through the valve. There is a valve at the bottom of the tank which causes the adding of the water through an upward seepage. The rate of the water supply is kept in constant. The loss of head caused by the upward seepage between the levels of A and B is small letter h. So meaning to say, the rate of the water supply in this tank is constant, and the loss of head here is denoted by h, small letter h. This small letter h is the loss in head that is caused by the upward seepage between the levels point A and point B. So small letter h is the loss in head caused by seepage between point A and point B. So the total stress at any point in the soil mass is due to the weight of the soil of the water above it. So meaning to say, if you're going to compute now for the total stress at any point in the soil mass, that is equivalent actually to the weight of the soil and the water above it.